Welcome to Mrs. Mahoney's podcast 2.3. We're going to be talking about heat transfer today. First, I need to apologize. I ran off on Friday. I think I was as excited as you guys to get out there and forgot what I needed to have from my podcast, which means my packet and packet on the computer. Also, though, kind of an added benefit, I looked through those packet problems on Friday when I was working them while you guys were shaking, and they were actually a little harder than I wanted to do, so I am supplementing them with some new problems. Now, two things. You can either stop this. I've loaded this sheet on Digital Locker, which you can access from your online gradebook, so you can go and reprint this, or you can just kind of scratch out the problems that are on there on your packet and kind of take the time and rewrite these and look at what it says. Or you can just kind of work the problems, and then I'll have copies of these on Monday if you want to add them to your notes. But these two problems, there's only two problems that I'm going to be working today, are more on the level. These two problems are more on the level that I expect you to be able to work, and some of the ones on the packets that if we had maybe more time to work and to handle on heat transfer than we'd be able to do, but for right now I just think the algebra got a little bit too much for what I really want to do in one day. So let's just look first at heat transfer. Heat transfer is just really the energy transfer between objects of different temperature. Probably help if it says not energy transfer between objects of different temperature. So when you have a transfer, though, the heat lost it's not lost. It's just being absorbed or gained by one other object. When you're cold and somebody's really hot next to you, they'll grab your hand or put their hand on you, and you can feel they're just transferring their warmth to yours. So how's it transferred? It's being transferred from a high temperature. It's being transferred from a high temperature to low temps. Warm is going to make the other person cold. The warm person will be warming up the cold person. Now the person who was warm to begin with is going to feel colder, but it's not because they transferred the cold to them. They're losing their warmth. So they're going to feel colder because they're losing the warmth. Okay, we can use this concept right here to solve what we call calorimetry problems. What a calorimeter is, it's just a piece of equipment that's made out of a non-conductive, so energy can't flow through it. We typically use styrofoam, something that's going to store the heat, so the heat of the system is not lost. This is how it will look. So let's look at what this problem is saying. I have a 25-gram sample, and it's heated to 100 degrees. And then I drop it into a beaker that has 90 grams of water, and it has my starting temperature. This is where my metal started. This is where the water started. The temperature of the water rose to a final temperature of 27.18. But do I have just water in here? This is also the metal's final temperature. They rose to an equilibrium. So the metal and the water both have the same final temperature. Then right here this statement, neglecting heat loss to the room and the heat capacity of the beaker itself. Okay, that's saying if we wanted to go into this, we would have to really say, but we're losing some to the environment, that beaker is absorbing some. We're saying, no, we're not. Let's leave this problem really easy, and we're only looking at two things, the metal and the water. So it wants to know, okay, what is the specific heat of the alloy? So really, I'm just going to have to do two heat problems. And so when I'm looking at my heat, we're using the same formula that we did on Friday. Q is mc delta T. I'm just going to do this once for the metal, and I know this is going to be equal then to mc delta T. This looks redundant, but this has to be done for the metal. This would have to be done for the water. So if we're looking, which one is losing heat? which one cooled down? So the metal lost, the water gained because it warmed up. This means this would be a negative because it lost, positive. So the only difference between this is the sign. The number is the same. So there's two ways we could work this. We can do it all at once as one big problem, or we could break it into two problems. So I'm going to do them both ways. First time I'm going to break them into two problems. So I figure out which one do I know everything? Do I know the mass of my water? Yes. Do I know my specific heat of my water? Yes. Do I know my change in temperature for my water? Yes. So I can calculate this first. So that's what I'm going to do. Q is my heat. I do not know that. What's my mass of my water? And it's right here, 90 grams. I didn't write this problem, but I'm going to say add a decimal so that we can get one more significant figure. So just add a decimal. Times specific heat of water. It's in our packet. We talked about it. It's a constant, 4.184. Okay, how much did that temperature change? Remember, final minus initial. So it was at 27.18. Then it went to 25. Oops, not going to do that. It went 25.32. Okay, you guys can write it on your paper. Obviously, it doesn't want me to write it here. I went off the screen, but you can just subtract. And so what is my answer? It went up 1.86 degrees Celsius. So that's just saying take your mass times your specific heat times your change in temperature. How much did it go up? It went up 700 joules. So that is the heat lost. Now I know that only has the one significant figure. And for now, we're not even going to worry about significant figures until we get to the end. And like I said, since I didn't write this, I'm usually going to give you at least 3 significant figures. So let's just go ahead and pretend that that has 90.0, and we'll give ourselves the 3 significant figures. I want to give you something with just one significant figure. Okay, so what does that mean? That means the water gained 700 joules. How did that happen? The metal lost 700 joules. So heat lost by the metal equals the heat gained by the water. So now I know Q for my metal. I know my mass for my metal. Specific heat's what I'm looking for. We just need to figure out how much did that temperature change for the metal. Well, it also ended at 27.18. But this one started at 100. So the metal went down negative 72.8. Again, that negative just means it was cooling, exothermic, but we know that. That's why it has a negative here. So now we're just plugging our formula in using the values for the metal. Negative 700 joules of energy. The mass is 25. Specific heat's what I'm looking for. The temperature change, negative 72.8. So I need to isolate X. So we're going to move these two to this side. You can either do the math first, or you can do it as one. This is making sure that you have it in the parentheses. Again, this is your algebra. You need to decide how you like to solve for your algebra. X, then, and because I gave myself that third significant figure, we'll give our answer in 3 significant figures. 0.385 joules per gram degrees C. It's not a new formula, we're just applying our other formula in a different way. Heat lost equals heat gained. When I talked about conceptual questions on the CA on Thursday, this is definitely a concept I would expect to kind of see, that you're going to have to realize heat lost equals heat gained. And sometimes it just might be an easier question like that. It looks like it might be a math question. Is it a conceptual question? That's what you guys need to really figure out. So let's look at this problem number 2. I have a piece 101 grams, so I know a mass of a metal. It's at 50 degrees, so I know what temperature it started. It's placed in 40 grams of water. That water is initially at 25 degrees Celsius. Then what's going to happen? The metal is going to cool down, the water is going to heat up, and then it reaches that equilibrium temperature, 29.7. That's the final temperature for both. I want to know what the unknown metal is. Well, the unknown metal, I remember I was saying intensive property, specific heat is an intensive property, you can use it to identify. So if I find the specific heat, we're going to match it up to that. You can use specific heat to identify metals. So we're just going to do the same thing, but this time I am going to just do it all at once on one worksheet, or in one problem. So I just know that I have mc delta T equals mc delta T. This is going to be a negative value because it's lost when I'm looking at that. So I go through, what do I know of all of these? So I have my mass of my metal, 101 grams. Mass of metal. Specific my metal, that's what I do not know. Okay, temperature change of the metal. So remember when you're entering these, metal on this side, water on this side. So the numbers need to be about the metal. So what did the metal? It was at 50, went to 29.7. Doesn't like me doing decimals. Minus the 50, and again, let's add a 0.0 for sig figs. So what was the temperature change? Minus 20.3. So this was a minus 20.3. Looks like, wait, it's going to be negative, but remember, this whole quantity is negative, so that makes the two negatives cancel out. Now for my water, what do I know? There's 40 grams. Again, let's add a 0.0. What's the specific heat of water? Now this is where I even went, oops, wait, stop. This is in calories. Specific heat that we usually know is in joules per gram degree C. Okay, calories is just another name for energy. We're not going to freak out because we know how to handle this. Oh, dimensional analysis. I know that 1 calorie is 4.184 joules. So therefore, it's just specific heat in calories is just 1 calorie per gram degree C. So 1 calorie per gram degree C. And see, these are grams, so they're going to cancel. Temperature change for the water went also, it finished at 29.7, but the water started at 25. So the water only changed 4.7 degrees. Now look at this right here. It shows you again the difference in specific heat. Metals have a low specific heat, so they have a large temperature change. Water has a high specific heat, so it has a small temperature change. If I can get my decimal, it just does not want to put a decimal. Okay, so I'm going to plug in 4.7. Now I can do my math all at once. Now remember, looking at this isn't a plus sign. It was a negative that made a positive. These are all multiplying. Everything's being multiplied and divide. Get x by itself. So I need to divide it by this quantity, the 101 times the 20.3, divided by your 101 times the 20.3. Again, I'm just isolating x, and you get that x is 0.092 calories per gram degree C. And again, you should be working these with your own calculator to make sure, especially right here, you can do this math. Make sure you get the algebra. So now if I know the specific heat, use this list. Which metal is it going to be? Barium, no. Chromium, no. Copper, yes. Right there. That's our answer. Therefore, my sample is copper. I was going to just write the symbol, then I changed it to write the name. Is copper. So tomorrow, Monday, we're going to be doing a gizmo that you're actually doing this kind of an experiment. And again, the reason we're doing the gizmo, we get better results. I've done it on a true lab and our results haven't been very good, so we're going to use the gizmo and try to see if we can actually see what we're doing on this math and do a simulated experiment. See you on Monday.